Okay, so let's start the class. So today we're gonna start talking about transversality. So let's just recall from last time that if I have a map from one manifold to another, so this is a smooth map between manifolds, and I take a regular point, a regular value on the target, then the pre-image of A is a submanifold of X. Okay, and actually I didn't quite say that explicitly in the lecture, but if you put dimensions here, if X has dimension n and Y has dimension m, then this is a submanifold of dimension n minus m. Okay, so we'll see later, but what the point is that the codimension of A is preserved. So the codimension of A is m, and the codimension of the submanifold is also m. Okay, so this is, and the proof was very simple, a very simple application of the implicit function theorem. So this is by the implicit function theorem. Okay, any questions about this? No. Okay, so now, you know, the main question is, how easy is it to get regular values? So are they really abundant or not? And the answer is yes. And I think you all remember the statement of Sart's theorem from the introduction, and that's the goal of today. So the goal of today is to prove Sart's theorem. Okay, so to be able to state Sart's theorem, I have to recall what it means for a set to be of measure 0. So if you have taken a measure theory class, maybe a lot that I'm going to say today is going to be elementary, or you're already going to see, but I'm not going to assume that you know measure theory, so I'll recall some of the important things so that we prove Sart's theorem. So, well, let me just state the theorem before, and then as we will actually define what we need to understand the statement. So the theorem says, if you have a smooth function, then the set of critical values has measure 0. Okay? So the set of critical values, I'm going to define that in a little bit, but that the critical values are the opposite of regular values. So a set that has measure 0, it actually can't contain any open sets. So that means, in particular, the set of regular values is not only non-empty, but it is dense. So it's very different than regular values. So near any point in the target, there is a neighborhood full. There is always a regular value that's as close to it as you would like. Okay, so this is the theorem that we're going to prove today. But before that, let's recall what it means to be of measure 0. So let me. Yeah, so I'm going to say if C is a cube, I'm going to do open cubes. So let me write A, B to the n. So this is the set of x1 through xn in Rn, such that xi is less than A and less than B. Xi is bigger than A and less than B. Okay, so I say the volume of the cube is just B minus A to the n. You could do this with rectangles and then just specialize to cubes, but I think it's just easier to do directly with cubes. And now we can define we say that a set of Rn has measure 0 if there exists an open covering if for every epsilon there exists a covering that I'm going to call Ci of S, where Ci is a cube. Well, it has to be countable. So it's an infinite countable. It could be infinite. It's a countable covering, where Ci is a cube, an open cube, and the sum of the volume of Ci, so this is actually a series, this converges and is less than epsilon. Okay, so if you can always find a covering by open cubes whose total volume is less than epsilon, that's what it means to be measured zero. You could do this with rectangles, and you can say, well, you might as well just look at cubes. Okay, so the first proposition is, well, a countable union of sets of measure 0 has measure 0. And the second thing is, if I have a function from Rn, or from Rn or a subset of Rn to Rn, and S is some subset of Rn of measure 0, then the image of S also has measure 0. Okay, so the first statement is quite easy. So if I have a countable union of sets of measure 0, so if I have Sn and each Sn has measure 0, so I can, for each Sn, I can choose an open covering with cubes. I'm going to call it Cin. I think someone's trying to come in. Yeah. Cin, such that the sum of the volume of Cin is epsilon over to the n. The sum for over I. Okay. So then, now I can consider the collection Cin for I and n, going from 1 to infinity. So this will be an open covering by cubes of the union of Sn over n. Moreover, if you take the sum of the volume, so if you take the sum in I and n of the volume of Cin, this is going to be the sum of epsilon over 2 to the n over n. So that's equal to epsilon. Okay, so that's the proof of the first one. So a countable union of sets of measure 0 has measure 0. And then the second part is, if I have a function from Rn to Rn, and I take a set of measure 0, then its image also has measure 0. Okay. So the first thing to notice is actually we can assume that S is contained in a compact set. And why is that? Because, well, you can, Rn is equal to the countable union of compact sets. So for example, you can take balls of, closed balls of integral radii, or you can take, I don't know, cubes. There are many, many different ways. So if you intersect S with any of these compact sets, then you have another set of measure zero contained in a compact set. I didn't say this, but it's pretty obvious that a subset of a set of measure zero also has measure zero. So we might as well assume that S is contained in a compact set. And this is something that we will do very often. We can assume in this class today that S is contained in some small enough neighborhood. Okay, so S is contained in a compact set. So now we can, what's good about that? The good thing is that we can, oh, I forgot to say, you have to assume F is at least C1. I mean, every time I write a function, it's almost always going to be smooth. But let me say that you actually only need it to be C1. And the reason is if it's C1, then you can write that the difference by the mean value theorem, if you look at the norm of the difference between f of x and f of y, and I'm going to be slightly slick, and I'm going to write just the norm infinity. But I think, you can write any norm, and then you're just going to have an extra constant. This is going to be k times the infinity norm of the difference of x minus y. Okay, someone's trying to come in. All right, so yeah, we have this inequality. So now because S, so this is for every x and y in S, and that's because it's contained in a compact set. So the norm of the derivative is bounded in the compact set. Okay, so now we can find a covering. So there's a covering Ci such that the sum of the volume of Ci is less than or equal to epsilon over k to the n for a fixed epsilon. Okay. So now notice that, because of this inequality here, f of Ci is contained in a cube Ci tilde of size of side length k times the sides of Ci. So Ci has some kind of side, and then I multiply the side by k. Okay, at most. So that means that the volume of Ci tilde is equal to k to the n times the volume of Ci. So, and then clearly, f, so now f of s is contained in the union of f of Ci, which is contained in the union of Ci tilde. Okay, and moreover, by this fact here, the sum of the volumes of Ci tilde is going to be equal to k to the n times the sum of the volume of Ci, which is less than or equal to epsilon. Okay, so that's so that proves that f of s has measure 0. So f of s has measure 0. So given an epsilon, I can find an open covering by cubes such that the total volume is less than epsilon. So actually, I forget if I've been saying less than or equal to or less than. Doesn't really matter. I did less than. So let's just, I think here I want less. And here's going to be less. Okay. Any questions? This is the proof of the first proposition.
So you just need Lipschitz for this?
Yes, actually.
Okay.
Yeah. Yeah, but as I said, we're really gonna use C infinity. Most of our functions will be C infinity, and this is really not an analysis course, so this is a lemma that will be used in manifolds. So I think the reason I didn't even say Lipschitz is because we haven't even talked about Lipschitz manifolds. I don't know really if that makes a lot of sense. So it's basically differentiable manifolds are the transition functions are at least C1.
Okay.
Okay, so now that because of this proposition, now we can define what it means for a subset of a manifold to be of measure 0. So let X be a manifold. And when I say manifold, again, unless I say explicitly, I always mean a smooth manifold. Okay, I'm not going to write this every time. If I start doing that, I will forget at some point. So let me always assume manifold is a smooth manifold with a chosen smooth structure. And if I consider a subset of X, then we say S has measure 0 if there exists an open covering UI, which is countable, of S, such that UI is contained or is the domain of a chart Pi that goes from UI to Rn, and the image of the chart of UI intersected with S has measure 0 for all I. Okay? So this definition makes sense because of the proposition that I just showed to you. Okay, so that means, in particular, this definition does not, S being measure 0 doesn't depend on which open covering you choose. And it doesn't depend on which chart you choose either. Okay, because if you choose a different chart, then you have another map from a transition map from Rn to Rn, and we know that maps from Rn to Rn preserve the property of being measure 0. Okay. So this also means that if you want to prove basically anything about manifolds of measure 0, you can always go look at a neighborhood, a sufficiently small neighborhood, and a chart, so you can actually look at the property in Rn. So that means actually everything else that I will say today about Sartre's theorem will be done just in Rn. We don't really need to consider manifolds. But we can have the statements for manifolds, but the proofs will all be local. Okay? So a corollary of this that I think is worth stating is that if F is a smooth map from manifolds Xn to Yn of the same dimension and S has measure 0, then f of s also has measure 0. Okay. All right. Okay. So now let's prove another proposition, which is the following. So if x is a submanifold of y, and x has dimension n, and y has dimension m, if n is strictly less than m, then x has measure 0 in y. So a submanifold of codimension at least 1 always has measure 0. Okay? So how do we prove this? Well, as I said, everything is local. So locally, we can see a submanifold as just a subspace Rn as a subspace of Rn, so locally. Okay, so as I said, if you want to prove something about manifolds, you can cover it with a countable number of charts, and in such a way that if you want to prove anything for the whole manifold, you can do it for each chart, and it'll have measure 0 too, at least when you take the union. So it suffices to look at this locally. So locally, a submanifold is just an Rn inside of an Rm. So how do you prove that Rn? So the statement is, the claim is that Rn has measure 0 in Rn. And here, n is strictly less than n. Well, how do you do this? Well, you can cover Rn. So first you start, I guess a picture is enough. So you can take your Rn, say that you can cut it in cubes. So I'm just gonna, I guess I can draw a picture. So you can cut it in cubes, maybe if you want of the same length. Well, to be really precise, yeah. Well, this is why it's better to do with rectangles. But I defined it with cubes, but I'm going to prove it using rectangles, and then you can subdivide the rectangles in cubes later. So anyway, so if you can take your Rn and cut it in cubes of small length, or actually of any length, of a fixed length, and then you can take each cube and you can multiply it by say, the minus epsilon, but actually, let me write it like this, minus epsilon i, to the m minus n. Okay, so you do that. That is like thickening your cube and making it into a parallelepiped in Rm, like a higher dimensional rectangle. Okay, so this is a parallelepiped. Parallelepiped. I think that's how you write it. Anyway, and then it's easy to see that this guy is going to have very small volume. So the volume of this guy is equal to 2 epsilon I times m minus n, raised to the m minus m, times the volume of Ci. And since Ci is the sum of the volumes of Ci is, no, that's, sorry. What you do is actually first you choose a fixed a fixed cube in Rn. So you do this for every compact set. So then the sum of the volumes of the Ci is actually finite. Okay, so you can suppose this is equal to some number, some finite number R. And now what you need is you need to show that the sum of these guys times R is less than a given epsilon. So you can always do that by just choosing epsilon I, for example, to see to be like 1 over 2 to the I or something like that. Okay, so you want your epsilon i's to be as small as possible. But anyway, the idea is very simple, but maybe writing it requires a little more. So anyway, let me say this one more time. So how do you prove Rn has measure 0? Well, you can split Rn into a countable union of cubes in Rn. So I'm drawing squares. They're all compact. So for each of them, you prove that they have measure 0. So how do you do that? So you take that. Actually, that's even easier. Sorry, this proof is even easier because you can take one cube and you can split it like this. Well, you can just take a cube and multiply it by epsilon minus epsilon. It's even easier. And the volume of this guy is to the m minus n is simply 2 epsilon to the m minus n times the volume of C. Okay, and then this guy can be as small as you want. Okay, and then you just use the fact that this is a union of countable sets of measure 0 has measure 0. And again, if you really want cubes, you have to be just a little bit smarter about splitting this up in cubes of the appropriate length. Okay, any questions about this? So if you've never seen this before, maybe this I'm going a little fast, but yeah, but it's really, there's really not a lot here. Okay. Anyway, this is the end. Any questions, comments? So a corollary of this is what we can call mini-SARD. Mini-SARD. So this is the easiest, sort of the easy part of SARD's theorem, which is that if you have X and Y manifolds, and N is less than M, and F is a smooth function, then the image of X has measure 0. Okay, so how do you do that? So if you take the image of a manifold in Rn into a manifold in Rn, m-dimensional manifold, and this has measure 0. Well, if F was an embedding, then this is a consequence, a directly consequence of the proposition. Okay, because if F is an embedding, then the image of X is a submanifold of the same dimension as the domain. So then it would have measure 0. But the point is that this is true even when you don't have an embedding. So for any function, this is true. Okay, so well, how do you prove that? You just kind of, you write F as a composition of something with an embedding. So it's just an observation that you can write F tilde X times R to the m minus n into Y. So F tilde of X A is F of X. Okay, so now you can look at X times 0 inside of X times R m minus n, and this is now a set of measures 0. So X times 0 is a submanifold, so this is a set of measure 0 in x times r m minus n by the proposition. Okay, so this is a submanifold, and now it's kind of clear that, well, f of x is just f tilde of x times 0. Or, times anything, actually, but in particular times 0. Okay, and f tilde is a map that takes a manifold of dimension m to a manifold of dimension m. And we saw in the previous proposition that these maps take sets of measure 0 to set of measure 0. So let me just point out here, this proposition here. Actually, it has a corollary. Yeah, right here. We're using this corollary now. Okay, so the conclusion is that this now has measure 0. Okay? And then now I'm going to actually have an exercise. And actually, one of you wrote down, solved all the exercises from last week and handed them to me. That's nice. So you can make your own problem set too as you go by solving all the exercises in the class. So feel free to do that. When I write exercise, you can also do that. So the exercise is that if you have an open set in Rn, then U does not have measure 0. In particular, or maybe let me just write hint. The hint is the following. So if C is a cube, an open cube, in Rn, and Ci is an open covering of C by cubes, then the volume of C is less than or equal to the sum of the volumes of Ci. So if you cover a cube by open cubes, then the sum of the volumes has to be bigger than or equal to the original volume. So, and because any open set contains an open cube, then there's no way to get an open covering with arbitrarily small volume. Okay, so if you've taken measure theory, maybe this is all trivial, but I think some of you have not taken measure theory. Okay, so with mini-SARD seems like, okay, this is not extremely hard so far. You're just saying that if you take a function from a manifold of smaller dimension than the target, then the image is going to have measure 0. Okay, this is cool, and because of this exercise, that means that the complement of the image, so corollary of the exercise, is that if you take the complement to the image, this is dense in Y. Okay, so it's very easy to find points that are not in the image of a map that goes from dimension n to dimension m, where n is less than m. Okay, so now I can prove a corollary of mini-SARD is what I'm going to call the easy Whitney embedding theorem. So this is the easy Whitney embedding theorem. And this says the following. So if X is a manifold of dimension n, which is compact, I need this condition of being compact, then X embeds into R2n plus 1, and X immerses into R2n. Okay, so you can always find an embedding of X into R2n plus 1 and an immersion of X into R2n. And what, this is easier because of the condition of compactness. So if you don't have compactness, then you have to talk about the Witten topology, which is what we're going to start doing tomorrow. But today we can prove this, this easier theorem. And sort of the hardest part of this theorem is actually to find one embedding into some Rn for some large Rn. So the first step is to embed X into some Rn or N very large. And this is where you really need the compactness to make it somewhat easier. So how do you do this? Well, first, you know that we can find charts, found a countable collection of charts. But actually, this gives rise to a finite collection of charts. Because of compactness, covering X. So basically you have phi from ui to Rn. These are charts. And I goes from 1 to say k. Okay? So what happens is, so these phi's, they are embeddings. And what you actually want is you want a little more. You want these charts, and you also want some a sub how do you call it? So you want a sub covering of UI, such that VI is contained in UI bar, and such that VI is still a covering. So this is pretty standard. This is what you do to, for example, get partitions of unity. So here's UI, here's VI. So you want to choose these charts such that VI is still a covering of X. And the reason you want to do that is, so you have this embedding, and you want to multiply phi by some bump function. So that this embedding can be extended. So Ci is a bump function. Such that Ci is always 1 on Vi, and so that the support of Ci is contained in Ui. Okay, so why do you do that? You do that because when you multiply Ci by Ui, no, by Phi, then this can be extended, to a map Vi tilde that goes from all of X into Rn. And this map is equal to phi when you restrict it to Vi. So this phi tilde restricted to Vi is an embedding. Okay? And then now you can patch these together, so you can basically take the product of all these maps. So now you consider a map phi, which goes from X into Rn times k, or Rn times Rn times Rn k times. And this map simply is, so phi of p will be phi1 tilde of p up to phi k tilde of p. Okay? And because Vi is a covering of X, then for every p will be in the domain, it will be in one Vi. So at least in one. So that means that there will be at least one of these functions here where you actually have an embedding. So this implies that phi is itself an embedding. Okay, so look locally, you can always find, for each p, you can find one of these i's here where phi I tilde is an embedding near that p. So that means that the capital phi here will be an embedding. Okay, so that's the first step. So to embed x into Rn for some n very, very large. And then the second step is to reduce the n. Reduce n. So you do that one by one. So the idea is, well, if you now you have a submanifold, you can think of x as already embedded into some Rn. That already solves the question, at least for compact manifolds, whether they all embedded in Rn. We know by this that they are. But what Whitney claims is that you can actually embed it into a relatively small Rn, where n is twice the dimension plus 1. So how do you do that? Well, so first, well, you look at x, and the idea is that you choose some direction to project. So now you project it to Rn minus 1. And here's your new projection. Okay? So you project it along some direction. So you choose a direction A, and you project along A. So well, what do you need to make sure that the projection is still going to be an embedding? Well, you need that the projection, that when you look at this projection and you restrict it to x, that this map is one-to-one. So for each element in x, there's a unique projection onto Rn minus 1. So what you need is first, you can't have two points in x that are that have the same direction where the difference is a, is a multiple of a. And then you need this to be an immersion as well. So basically what you do to be able to do that is you look at the map G that goes from x times r to Rn. Let me call this first embedding f. So f is the embedding from x to Rn. And I'm trying to find a good vector A in Rn to project along. Okay, so for those of you who forgot what it means to project along, it just means that you choose an A. This is like the orthogonal projection. And I'm going to project orthogonally to A. So if A is some point in Rn, then the orthogonal complement is a copy of Rn minus 1. And I'm going to project my manifold X along A, orthogonal projection. So I'm to find such an A, I'm gonna first look at this function G. And what's the function G? Well, it's basically what it's gonna do is it's gonna try to prevent me from projecting on a direction where the projection would overlap. So I'm gonna consider the function G to be t times f of x minus f of y. So the point is, it's easy to check, and maybe I can call it an exercise, but this is an easy exercise, is that if A is not in the image of G, then the projection along A of x is, well, projection of A composed with F is still injective. Okay, so if A is in the image, and you can see that it's not injective. So this is the condition that you need for it to be injective. Okay, so if A is not in the image of this G, that means that if I take two different points of X, when I project it, they will be mapped to two different images on Rn minus 1. Okay, so, and then you consider another function, and now you actually, you want it to still be an immersion. So the function is just, h of x v is just the derivative of f of v.
Sorry, I got lost here. Who is f?
F is my embedding from x to Rn.
Was it phi?
Phi?
Yeah,
Oh, sorry. Yeah, it was phi. I just changed the name because I moved to second step.
Okay,
Yeah. So F is what I had called phi originally. No, the thing is that I'm actually going to do this by induction. So I'm going to be reducing. Maybe that's why it's not phi. So phi is just the first embedding into some Rn for n very, very large. And the second step is saying, if I have an embedding into some Rn, then I can embed into Rn minus 1. And I'm going to apply this over and over and over until I have to stop. Okay?
Okay.
Okay, yeah. So yeah, the first f that you start with maybe is this capital phi. But the point is that I'm going to be playing this game over and over again. So I'm embedding into some large Rn, and then I'm going to reduce the dimension by 1, then I'm going to reduce the dimension by 1, and for a long time until I have to stop. Okay.
Sorry, a remark. So if by minisard, if the capital N is bigger than 2n plus 1, then you have a dense open set of possible directions A.
Exactly. Yeah, that's the point. So yeah, but I mean, I have to. So I know that this is still injective, and so the second part is looking at this other function, which is the image of df of x, the image of the derivative. Okay, and the exercise here is to show that if A is not in the image of H, then H composed with F is still an immersion. Because being injective is not enough for it to be an embedding. You need it to be an immersion and injective. Okay? So now we can combine these two and say that if A is neither in the image of G nor in the image of H, then sorry, I actually wanted to say the projection along A is still an immersion. Then the projection composed with F is an injective immersion. And we saw last time that an injective immersion, I think this was an exercise, is an embedding if the domain is compact. So an embedding. Okay, and by minisard, if n is strictly greater than 2n plus 1, then we know that this set is dense, and this set is also dense. Okay, so the intersection of two dense sets is dense. Or you can go look at the other way around. The image is measure 0, and this image is measure 0, and the union of two sets of measure 0 has measure 0. So it's very easy to find something that's not in it. What you need to be able to reduce, you need that n is greater than 2n plus 1, which means that when you get to 2n plus 1, you have to stop. Well, you have to stop if you want it to be injective. But see, if you want it to be just an immersion, you can go one more time. Okay, so if you want the map to be an immersion, then you only need not to be in the image of H. And here, Tx is a manifold of dimension 2n. So if n is equal to 2n plus 1, then we can still find, and A, which is not in the image of H. So X still immerses into R2N. Okay? Okay, so this is the easy Whitney embedding theorem. So in maybe in 2 classes or in 3 classes, depending on how it goes, we will see how to do the same thing for manifolds that are not compact. And this is maybe called, I don't know, the medium Whitney embedding theorem. Because the really hard Whitney embedding theorem is saying that you can actually reduce one more dimension. So this is the end of this proof. And the hard Whitney embedding theorem is that you can actually embed X into R2N. So you can do one more dimension. And it is much deeper than transversality theorem. You have to be very clever with, basically the idea is you take your immersion into R2N and you have to resolve a potential singularity. Okay, so this you start from this immersion and then you have to resolve the potential self-intersection using something called Whitney moves. But I might talk about this at the end of the course if we have time. But this is beyond transversality. It's harder than that. Okay, so this is just a nice little application of what we've seen so far. Are there any questions?
I have a question.
Yeah.
Is it obvious that F is an embedding? F or phi?
Uh-huh.
Why is it?
Yeah.
Yeah. I don't get it. Why, if every phi is an embedding, then phi has to be 1.
So it's not that every phi is an embedding. So remember what you need to have an embedding is you need to be immersive and you need to be one-to-one.
Yes. Okay. Okay. I got it. Thank you.
Okay. You're welcome. Yeah. So it's not that every phi tilde is an embedding. If one phi tilde was an embedding, you didn't even need to consider this capital phi. So phi tilde is only an embedding locally. Okay, so phi tilde is only an embedding in some open set. But then globally, it's not an embedding. So globally, if you're very far from that, you're going to be 0. But the point is that you patch a lot of, you take the product of a lot of maps, which are embeddings in small neighborhoods, but the places where they're embeddings covers the whole manifold. Okay? Okay, and you have to check, but it's not very hard to see that. I mean, one-to-one is straightforward. And it being also an immersion is not very hard to check.
Okay, because being an immersion is a local property, right?
Yes.
So.
And if one function is an immersion, then if you put other coordinate functions, then it's still going to be an immersion because the derivative is something like this. So if you were in the kernel, if you're in the kernel of derivative, you have to be kind of in the kernel of everything. So if the kernel of one of them is only 0, then there you go.
Okay.
So the derivative, is a matrix like this. Okay?
Okay.
All right.
I understand now. Thank you.
You understand? Good. Thank you. Okay, so now let's go towards SARD. So the full SARD theorem. So let me just do a quick definition. It's something I kind of already said, but I haven't quite defined. So if I have a map, someone is trying to join. Okay. So if I have a map from X to Y, and I have a point, well, let me do the definition. So we say that a point P in X is a critical point if the derivative of f is not surjective. And we say that P is a regular point if the derivative is surjective. And then if we take a point in the image or in the target, we say this is a critical value if there exists a critical point such that f of x equals a. And a regular value if x is a regular point for every x in the preimage of A. Okay, so we had already defined regular values before. So I'm just defining critical points, critical values, and regular points. Okay. So there's just this little thing, like if you have a regular value is a point where is a value is a point in the target such that all the preimages are regular points. Okay, so there could be some values that are preimages of critical points and regular points, and these will still be called critical values. Okay, so I mean we can a common notation is to call crit of f the set of critical points. And the image of the set is the set of critical values. Okay, so now we can state and prove Sard's theorem. So Sard's theorem says that if you have a function which is smooth, then this set has measure 0. Okay, so a couple of comments. Remark is that using this definition, if I have a function from xn to ym, and n is less than m, then every point in X is a critical point. So that implies that every point in the image is a critical value. So this whole thing is a set of critical values. Okay. And this is why I called the previous theorem or the previous proposition mini-Sard, because the mini-Sard will say that this image is has measure 0. Okay, and I should also say an observation is that some authors have a slightly different definition of a critical point. So some authors define a critical point as a point x in x such that the derivative, the rank of the derivative is less than the minimum of M in N. So in particular, it encompasses the case of immersions. So a local immersion will still, the point for which the derivative is injective, for example, will not be a critical point, will be a regular point. Okay. So it's a slightly different definition in the case when N is less than M. But I prefer this definition. In any case, we usually use Sartre's theorem. Sartre's theorem is more interesting in the case when N is greater than M. So, I mean, it's maybe just good to know this, but we're not going to, in general, I think it's better to have the definition that I gave. Someone else is trying to? Oh, someone raised a hand. No. Okay, that was a mistake. All right, so now we can go and prove Sartre's theorem. Oh yeah, sorry, a couple more observation. Another observation is that we only need so we don't need to require the function is smooth, but there is a funny requirement actually in terms of the smoothness. So if you state the theorem for well, we only need F to be CL, where L is greater than the maximum of the dimension of X. Yeah, the dimension of X n minus M and 0. That's it's kind of funny, but if n is greater than M, then you can't do this for C1 in general. You can only do it for CL where L is sufficiently large. But if for mini Sard, you really only need L to be 1. Okay, so that's why this is this max. Okay, and I mean, I'm going to just do the proof for the smooth case. I'm not going to bother with this detail, but if you're very careful, if you look at what the proof very carefully, you can see where this condition comes in. Okay, so now let's do the proof. So the proof will be by induction on M. On N. And of course, we can look at the local case. So we just have a function from Rn to Rm, or from an open set. And I'm assuming this is smooth, and I'm going to prove that the image of the critical point set is of measure 0. So the claim is that f of the crit of f has measure 0. Okay. Okay, so the proof has 3 steps. So the induction, first of all, let's just see that for n, we start the induction in n equals 0, and then this statement is obvious, because for n equals 0, you just have a point. So the image of a point is a point, and a point has measure 0 for n greater than 0. Okay, so for n equals 0, this statement is trivial. So if it can, so then we can just apply induction. So I'm going to call C in this proof will be the critical, the set of critical points. Well, like now assume true for all f from Rn minus 1 to Rm. Okay. So, and maybe we assume m is greater than or equal to 1. So, yes. Okay, so I'm going to call C the critical point set, and then I'm going to define Ci to be the following thing. So this is going to be the set of points x in u such that all the derivatives, all the partial derivatives, delta L del x L of x is equal to 0 for every multi-index that whose size is less than or equal to I. Okay? So, C1 is the set of points such that all first partial derivatives are 0. C2 is the set of points such that all partial derivatives up to order 2 are 0. And should emphasize this is bigger than or equal to 1. Okay. Is that clear? So in particular, we have C contains C1, contains C2, etc. Okay. Yeah, so if I'm in C1, then I'm clearly a critical point. And so forth. But to be a critical point, I just need a derivative not to be surjective. So I don't even need all of the partial derivatives to be 0, which is why you might have something in C that's not in C1. Okay, so now we have 3 steps. So the first step is to show that Ci has measure 0 for sufficiently large I. The second step is to show that Ci minus Ci minus 1 has measure 0 for all I. And the third step is to show that C minus C1 has measure 0. Okay. Any questions? So as you see, it basically the reason we do this is because it's hard to show. Sorry, it's not Ci, it's f of Ci. The set of critical points definitely does not have measure 0 in general. Okay, so it's the image of the set of critical points that has measure 0. And maybe if you haven't thought about this, why is that true? Just, for example, take the constant function. The constant function, for the constant function, everything, the whole domain has measure. The whole domain is critical, and therefore cannot have measure 0 in itself. Okay, so it's only in the image that you can have the chance of having measure 0. Okay, so let's do the first step. Well, so in Ci, we have the following condition. We can assume as usual. So as usual, we can assume that Ci is contained in a compact set. Because otherwise, as I said, we can assume U is contained in a compact set, and let's just do that. Because otherwise, you can just take the intersection with a countable cover of Rn by open sets. And then if you're trying to prove something has measure 0, you can do it for each of these. So if you're in a compact set, then in Ci, we can use Taylor's formula, and that will mean that the difference between f of x and f of y will be less than or equal to some k times x minus y to the I plus 1. Okay, so this is by the Taylor's formula, and I can use any norm I want. I might as well use the infinity norm. Okay. So now I can actually can just take this to be a compact cube. So CI is contained in this compact cube. And now I can take my compact cube, say that it has a compact cube of side length B. So my U is contained in a cube of side B. So what I can do is I can subdivide B into cubes of side length B over R. So I can subdivide this cube into R to the n cubes of side length B over R. And the point is that f of Ci is now going to be contained yeah, that's right. So each of these cubes is now going to be contained in a cube Ci tilde. This is a cube of side length k to the n times B over R to the n times I plus 1. But I have R to the n such cubes. So that means that, oh no, sorry. Each of these cubes, so yeah, so let me call, okay, let me do this again. Okay, so I have cubes, let me call these cubes dk. Okay, so this means that f of Ci intersection with dk is contained in a cube dk tilde of side length. So if I'm in Ci, then this thing holds. And if I'm in dk, then the length of the side is B over R. So now what happens is the length of the side is, the length is going to be k to the n times B over R to the I plus 1 times n. But each of these, I have R to the n of these cubes. So when I take f of Ci, this is going to be contained in the union of R to the n cubes, the union of R to the n cubes of, oh no, sorry. The side length is k times this. Yeah. So the side length just gets multiplied by this. So R over B to the I plus 1. So R to the n cubes of side length k times R over B to the I plus 1. No, B over R. Okay, and then now I can look at, well, these are cubes of this side length. Now I can look at their volume. So the sum with the volume of each of these cubes, now this is in Rm. So the volume is going to be, if the side length is this, the volume is going to be k to the m times B over R to the I plus 1 times m. Okay, so the sum of the volume of these cubes in Rm is going to be, so I have Rn of these cubes, so it's going to be Rn times this number. So k to the m times b to the m I plus 1 over r to the m I plus 1. And here's the thing. So this is k to the m times b to the m I plus 1 times r to the n minus m I minus m. Okay? And the point is that this guy here is constant. This part here is constant. And this part here, as I goes to infinity, this, and as r goes to infinity, or if I is sufficiently large, as r goes to infinity, this goes to 0. So this can be as small as you want. And actually what you want, you only need n minus m minus mi to be less than 0. That's the condition that you need. So you don't even need to take I very large. It just, the condition is that I plus 1 is greater than or equal to n over m. This is all you need. Okay. And this is where the condition of it having to be CL for L sufficiently large comes in. Okay. So that's the end of the first step. Okay, so we proved that f of Ci has measure 0 for I sufficiently large. Any questions? Okay, so second step is we have to look at the image of Ci minus Ci plus 1. Okay, so if you have a point, if x is a point in Ci minus Ci plus 1, that means that there exists some I plus first partial derivative, which is non-zero. But all the partial derivatives up to order I are equal to are 0. So there exists some ith partial derivative, and I'm going to call that g. So this is some ith partial derivative. So this goes from Rn to R, such that g of x is 0. G of x is 0. And dx something, let's suppose it's x1 of x, is different from 0. So we can suppose that without loss of generality. Otherwise, we can switch the orders. Okay, so now we can use the implicit function theorem. So by the implicit function theorem, there exists a local diffeomorphism, maybe U prime contained in U, a local diffeomorphism such that the image of Ci minus Ci plus 1, well, intersected with this U prime, is contained in 0 times Rn minus 1. So that means that if you change up to a change of variables locally near x, if you want to keep this condition of g of x is 0, which is what you need to be in Ci, so the image of Ci minus Ci plus 1 is taken to 0 times R of n minus 1. Okay, so this is what the implicit or the inverse function theorem, however you want. And maybe this is maybe an exercise for those of you who are not so comfortable using the inverse and implicit function theorem, is understand this last statement. You don't have to write this down, but So if analysis on Rn is very easy, for you, then maybe this is completely trivial. But maybe you wanna think this a little more. So rewrite what G is. So and figure this out. But I think shouldn't be too hard for you to understand. But you can ask me a question if you want to. Okay, so now basically if you write K, which is F composed with this H inverse and restricted to 0 times Rn minus 1, this is now mapped from Rn minus 1 to Rm, or from maybe some neighborhood of Rn minus 1 to Rm. And the image of Ci minus Ci plus 1 is, it's more than this. It's actually contained in the critical set of K. Okay, so if your critical if your critical point of F then you have to be a critical point of K. Okay? And then now we can use the induction. So by the induction hypothesis, the image of the critical point set has measure 0. So the Ci minus Ci plus 1 is contained in this guy, or at least intersection with U prime is contained in K of the critical point, in the critical values of K. And that's it. So remember I told you that we would use this over and over again. So if you want to prove something has measure 0, and you can prove that for every point you can intersect it with the neighborhood of the point and that has measure 0, that's enough to show the whole set has measure 0. Okay, so that's the second step. And the third step, well, so for the third step, we're going to need a lemma. And the lemma is Fubini. Fubini's theorem for measure 0. So any questions? Are you guys still there? I haven't heard anything. Well, it seems like you are.
Yeah, we are here.
Okay.
I don't understand why. What's the relationship with the image of K of crit of H?
K of crit of H. No, K is of crit of K. Yeah.
What? But why is that the same as F of Ci minus Ci plus 1?
Well, because K is the composition of F with H inverse.
Okay.
Yeah. So wherever it's defined, F is equal to K composed with H.
But it is defined on a smaller neighborhood, right?
Yes, exactly. Yeah, where it's defined.
What happens with the rest of?
That's what I was saying.
Okay.
So for each point in Ci minus Ci plus 1, there is a neighborhood around it, so that the intersection of this neighborhood has measure 0.
Okay.
Yeah, but because of the condition of set countability of manifolds, or whatever you want, you can cover it with a countable set of measure 0 sets. Yeah.
Thank you.
Mm-hmm. Okay, so the third step is Fubini's theorem for measure 0. So it requires this lemma. So the lemma is the following. So let A be compact such that when you look at a slice, such that A intersection with X times Rn minus 1 has measure 0 for all X in R. So it has measure 0 in Rn minus 1. So in X times Rn minus 1 for every X in R. Then A has measure 0. And another way of saying this in terms of measure theory language is that if the integral of the characteristic, if the integral of 1 over A dx1 dxn, this is equal to the integral of 1 dx2 dxn, A intersected with X times Rn minus 1, and then you integrate dx over R. And if each one of these is 0, then this thing is 0. That's why this is called Fubini's theorem. And this is it's the easiest case of Fubini's theorem. Again, if you've done measure theory, you've seen this in much wider contexts. But anyway, let's prove this lemma. It's not so bad. Well, how do you do that? Now, first of all, if A is compact, you can just assume A is contained in AB times Rn minus 1. So you only really need this condition in a compact set. And then now, so for each X in AB, there exists a covering by open cubes that I'm going to call C1x up to CNXX of the slice. Actually, sorry, let me be more precise. Since we're doing basic measure theory, I better more precise. So my open cubes are well, let me say the following. They're open cubes. There exists open cubes C1x up to CNXX. These are open cubes in Rn minus 1, such that A times X times Rn minus 1 is covered by X times C1x up to X times CNX. So it might be better to just like forget about the X and project everything to Rn minus 1, but anyway, I didn't do it. So we have to multiply everything by X. So the idea is, here I have my X times Rn minus 1, and I have my A, which is some set, and when I intersect it with this, I'm covering it with cubes like this. Okay, and an exercise. This is a basic analysis exercise, general topology if you want, is that if you move X a little bit, then you're still going to get a covering. So the exercise is, in other words, there exists an open interval Ix inside of R containing X such that Ix times Cnx for n between 1 and nx is a covering of A intersection Ix times Rn minus 1. So in other words, if you take these cubes in Rn minus 1 and you move them around in this direction, in this R direction, they're still going to cover this intersection. And that's because of the openness. This is a general topology exercise. Okay? So this means that we get an open covering the open covering is Ix times Cnx for x and n of A. But since A is compact, we can find a finite subcovering. So we can find, basically we can find a finite number of x's such that we can get an open covering. So we can find a finite subcovering Ix times Cnx. Now the n and the x are finite. So the n goes from 1 to some big nx. But now the x is contained in some set that I'm going to call B, where B is a finite set of points set in, say, AB. So we're almost done. Now, clearly, this Ix, it has to be, in particular, this is a cover. This covers the interval AB. And now you can look at the lengths of this Ix. And the length of each of Ix is, basically the difference of the 2 points. But an exercise, one more exercise, is that up to a refinement, the sum of the lengths of these Ix's is at most twice B minus A. Okay, so basically, if you have an interval AB, and if you cover it with open intervals, the exercise is to say that, well, up to some kind of refinement, taking slightly smaller intervals that still cover the whole thing, one for each, the sum of the lengths cannot be, actually, you can even prove it's strictly smaller than 2 times B minus A. So this means, just to finish, that A is covered by these parallelepipeds, whose volumes, so the volume of a parallelepiped like that, is equal to the length of Ix times the volume of C and X. Okay. And because we assume that the slice A intersection with X times Rn minus 1 is of measure 0, we can assume that the Cnx is the total volume is less than epsilon. Did I do that? Yeah, I forgot to say this, but of course you assume that the volume of C and X, the sum of that, is less than epsilon. So the conclusion is that the sum of the volumes of these new neighborhoods is less than 2B minus A times epsilon. So you can make it as small as you want. So A has measure 0. Okay. Any questions about this?
Hello.
Hi.
I have noticed. A detail.
Yeah.
Uh, can you can you go to the end of the proof of the second step?
Yeah.
I think in the last line you
Mm-hmm.
need like you need to consider f of ci minus ci plus one intersection
Oh,
u prime.
sorry. Yeah, you're right. You're right.
Okay, and also I have another question. Like you have proved this from well, you're considering u prime, but what happened outside this set? How can we?
Well, each point, so what you're trying to show is that the image of Ci minus Ci plus 1 has measure 0.
Okay.
So you take one point in the image. So if you want to consider the image of all of that, then you can just consider the image of Ci minus Ci plus 1 intersected with any open set. With a sufficiently small open set. So if you can just look at any point first, and you show that any point has an open neighborhood, such that let me actually fix this. So this is what you're proving. Sorry for
okay.
yeah. So for each point in Ci minus Ci plus 1, you prove that there is a neighborhood such that the image of that has measure 0. So you can cover that with countably many sets of that form, and you have your statement.
Yes. I got it. Thank you.
You're welcome. Sorry, this is a little twisted, but okay. Let's just finish the proof of Sart's theorem. So so finally, the step 3. So which is to show that f of c minus c1 has measure 0. So how do we do this? Well, you take a point. I'm going to call it point, P, point in C minus C1. So that means that you're a critical point, but there is at least one partial derivative that's not 0. So without loss of generality, we can assume, we suppose, that it's d of f1 of d of x1, b, which is non-zero. Okay, so you can otherwise you can switch the order, and again by the implicit function theorem, or maybe in this case is more like the inverse function theorem. Well, they're the same theorem. Up to a local diffeomorphism, we can assume that f of x1 through xn, it has the form of it. The first coordinate is just x1, and then you have something else, g of x1 through xn. Okay, so this is, I guess if you want, it's by the inverse function theorem. So if you consider inverse function theorem, and then yeah, so it's similar to what I said before in step 2. So now you see that the f at the point P is just going to be, we have 1, then you have 0, then you have something here, and then here you have the differential of some function, which I'm going to call g tilde, and g tilde of the point x1. No, sorry, let me write it like this. G tilde x1 at the point P tilde. And g tilde x1 is the function g of x1 dot. So this is a function that goes from some subset. Sorry, let me have space here. G tilde x1 goes from some subset of Rn minus 1 to Rm minus 1, and it takes p tilde to, or it takes x2 to xn to g of x1, x2 to xn. And here my p is just x1 p tilde. Okay? So one thing that you can check, given this expression of the differential, is that this critical point set is that P belongs to the critical point set of F if and only if P tilde is the critical point set of G tilde of X1. Okay? Of course, this is local. This is only in the neighborhood of a given P, but this is still true. Okay? So, and then also, yeah, you can check that. So now f of c minus c1 is contained in sort of the union over x1 of g tilde x1 of the critical point set. I can write it like this. X1 times g tilde x1 of the critical point set of g tilde of x1. There you go. Okay, so now you can see how to use the induction hypothesis. So by the induction hypothesis, this the set of critical values of g tilde of x1 always has measure 0. So this guy has measure 0. I should say it's usually empty, but it has measure 0. So when you take the union of that for all of the x1s, then this guy here, by Fubini's theorem, it has to have measure 0. So by Fubini's theorem, this guy here has measure 0. Okay, so again, this is local, so maybe this is written I'm writing in a little sloppy way, but I apologize for that. Okay, so that's the end of Sart's theorem. Again, this is not really a topology theorem, it's more of an analysis theorem, but because it's so important for this, for the transversality part, I decided to take the class today to prove it. And a corollary of this, of Sart's theorem, is if you have a smooth map, then the set of regular values of f is dense in Y. Okay. So that's the end of today's class.